Okay, let's do a simple example. We want to investigate a loop with a simple PT1 and our deadbeat controller. Yeah, deadbeat controller, and we want to have special values, say k is 3, time constant 0.5 seconds, and sampling time should be 0.1 second. Close the loop and have negative feedback. The letters of the loop should be desired value W, control difference XD, controller output Y, process output X, node in old docs, number smaller than 33. I have used the letter XR instead of Y at some position. So I have to exchange it. The controller output now should be always Y, and the process output should be always X. In some books, in some countries, we use different letters. Now I have changed my document to get all controller output letters Y. Okay, let's do our job. First, we need the process step response invariant filter function. We can do this with b1 z to the power of -1 divided by 1 plus a1 z to the power of -1. We use the following equations from chapter 9.2. Let's go to 9.2. Yeah. For the PT1 case, here you see A1 is negative exponent sampling time divided by time constant. It's A1. A1 is negative e to the power of minus sampling time divided by time constant. In our case, minus e to the power of minus 0.1 divided by 0.5. This is negative e to the power of negative 0.2, and we can calculate this value to 0.8187. Okay, then the B1 is k times 1 minus A1, or 1 plus, sorry, I have to look, 1 plus A1, 1 plus A1, so this gives 3 times 1, oh, minus sign, forgotten, 1 minus 0.8187, this gives finally 0.9063. We want to calculate with 4 significant digits. I've just typing error, sorry for this. The result is 0.5438. 4 significant digits. Okay, now we can calculate the or we can write down the algorithm to calculate the output values step by step. X of n is, the algorithm now is known, X of n is negative A1 is 0.8187 times X one step before plus B1 is 0.5438 times input value caused by the z to the power of -1 here, delayed by 1, n minus 1. Let's see, for process output values. Process output values. Now calculate the deadbeat controller parameters. The first parameter is Q0, is 1 divided by the sum of all b's. In our case we have only one b, so this is the inverse of b1. The inverse of b1 gives 1.839. Then we have Q1. Q1 is Q0 times A1. In our case, Q0, we store this for the moment, so Q1 multiplied with A1 is 1 times negative 0.87 gives negative 1,505, and the P1 is Q0 times B1, and in our case exactly if Q1 is 1 over B1, this is absolutely accurately the 1. So we can write down the controller transfer function. In our case is 1.839 plus a negative minus 1.505 z to the power of minus 1 divided by 1 minus z to the power of minus 1. Or the algorithm, if they say, okay, this is output y divided by input xt, the algorithm for the controller output y of n is, output is here with the number 1 is n minus 1 plus 1.839 x control difference actual value minus 1.505 control difference one step before. For controller output values. Okay, now we have the possibility to calculate for each step the output values of the process and the output values of the controller, depending on the control difference here and the desired value here. So what we want to do is just play with the closed loop system in that way that I calculate now the reaction on a reference step to calculate the reference step response of xt, y, and x. Let's calculate reference step responses on all signals x control difference, process output, controller output. For this I make a table for these single steps 0, 1, 2, and 3. I want to have the reference step, say unit step amplitude is given. Then if we have here a unit step function, in the first case, first step we know what happens if we jump here to 1 at once. Xt goes up depending on x back. What is x back? The feedback signal in the first microsecond is unchanged because the PT1 cannot jump at the output, or we have no B0. Yeah? So we can say the x value at 0, here we can see this also with this equation, x value is, old x value is 0, and here there is only a reaction of the y which is delayed. So y of n-1 is 0. We assumed, of course, 0 initial conditions. All signals before we do this should be 0. So we know the output of x in the first moment is 0. That means that the xt of xt, oh sorry, the table. Okay, xt of n, that is x of n, sorry. X of n, xt of n is 1. xt is always desired value minus actual value. So this is the difference of these both values. And with the 1, I can calculate now the controller output value in the first moment. So we use this equation. Y of 0 is y of -1 is set to 0. Initial conditions means this old value must be set to 0. This is 1 multiplied with our Q0, and this is still 0 because this is a step in the past. So we get 1.839 as the first impulse of my deadbeat controller output. Okay, so this was the first step. What happens? 100 milliseconds later, in step 1, we see the desired value is still 1. X of n must be calculated. Now let's calculate x1. x1 can be calculated with this equation, with this equation for process output values. So x1 is 0.8 and so on times x0. x0 was 0, so this is 0 plus 0.5438 times y of n is 1, so this is 0, y of 0 is our controller output 1.839, and you may believe it, this is exactly accurately with 1,000 zeros exactly V1. So we can write here a 1, and the control difference is 0. And now let's calculate the y1 value with this equation. y1 is old output one step before, this was our 1.839 plus 1.839 times actual control difference is 0 minus 1.505 times control difference one step before, this is this value, so this is a 1, and the result is 1.839 minus 1.505. This should be a 0.3333, yeah, with 1,000 digits, a period of 3. So this is 0.333. So that we can now look for the next step. So this looks good, yeah. The reference, the process output is after one step is our desired 1, but now this should stay at 1, and this should stay at 0, and we want to have the controller output which is necessary to stay at 1. So let's calculate for n2 the X process output value with this equation. This equation gives, this is 0.8187 times process output one step before, this is this value, so times 1, plus 0.5438 times controller output one step before, is our 0.3 period. And if you type this in, I have checked this. If you calculate with more than 4 significant digits, you will get also a 1. So this stays at 1. So with the control difference, this must stay at 0. And y of 2 can be calculated. Y of 2, where's the equation? Y of 2 is y of 1 is 0.33 period plus 1.8 times xd of actual value is 0 minus 1.5 times xd one step before, this is also 0, so this stays at 0.333 period. And you see there will be no change for the next steps. x3 is 0.8187, x2 plus this times 0.33, it's the same equation like this, so there is always a 1 at the output, so this stays at 1, this stays at 0, and then this stays at 1/3. If we look here, what happens is here we get a DC signal after input step of 1/3 times 3 gives a 1 here. So this is exactly that value that PT1 needs with a K of 3 to stay at 1. So the deadbeat controller does the following step. If we draw now the signals in a diagram on a time axis, say, okay, this is 0.1, this is 0.2 seconds, so this is N1, this is N2, 0. Then we see the Y value in blue is jumping on 1.839, stay one step at 1.839. So this scaling should here be 1, then this is 0.3 period, and the controller then goes back to 1/3 and stays constant. The process output value is calculated with 0 here, 1 there, 1 there. So these are only points at sampling times, but we know that this is the step response of a PT1. So we assume a curve like this, exponential function, and then stay here with constant line at this point. So what we can see is a curve which goes up with this speed caused by my Q0, my 1.8, in that way that exactly after one sampling time I reach the final value, and then the controller jumps exactly to that position where this value is held constant. So the miracle behind the deadbeat controller is really in one step, in a first order process, in one step, the settling time, one step is the settling time. After exactly 100 milliseconds, the final value is reached and without any overshoot, undershoot, then held constant. So this is the fastest possible way to shift the process output from 0 to 1. And this is exactly that value which is used to do this. Yeah? So this, I say, similar to that if you are preparing potatoes with hot water. Your heater is switched to full power. If you do this, put your potatoes in water, put it on a heater, and then normally you switch on the heater with full power, and in the correct moment you switch down to that heating where the water is still cooking, not overcooking, not going down. So then you have exactly the temperature you want to have. Yeah, that is a, yeah, in other words, the way the Delphi controller works. Okay, so far at this point, let's continue with the third video.